Thank you for joining us. We are the Lunar Dust Busters, and we're going to be presenting our Dust Shield Integration System, or DSI. My name is Elizabeth Campa.
Sorry.
Get rid of the meeting controls.
Yeah.
Control Alt Shift H.
That's okay.
Yeah, it's the floating meeting control.
Yep. Okay.
That's
Sorry.
Go
Thank
ahead.
you.
My bad.
So this is an outline of all the things that we're going to be covering further in depth, starting with the mission brief. With the Artemis missions that are on the horizon, there's new project incentives to create a device that's capable of mitigating the impacts of lunar regolith. And so our team designed a device for the Artemis 5 mission, which is going to feature Blue Origin's lunar lander called the Blue Moon Lander. And it's set to land on the moon's south pole with the main objective of collecting new samples.
I'm Katie. I'll be doing the background information on the lunar regolith. So to first understand the mission purpose, we want to understand why it's a problem. So the lunar regolith is defined as the fine layer of dust extending 5 to 10 meters below the surface of the moon. It has physical properties of an average particle size of 70 micrometers, with finer grains under 20 micrometers being classified as lunar dust. It also has a individual particle density of approximately 3 grams per centimeters cubed, and with a bulk density of 1.5 grams per centimeters cubed, which increases with depth. It is electrostatically charged from UV and X-ray radiation, and it has a surface area to mass ratio 8 times higher than spherical particles of the same size distribution here on Earth. There's many harms for the lunar dust and the lunar regolith that can be split into both human health hazards and mission and mechanical hazards. The human health hazards include watery eyes, decreased vision, cough and throat irritation, lunar dust embedded in the lungs, infections, heart failure, COPD, and lung cancer. The mission and mechanical hazards include functions of zippers, locks, buttons, all being affected, dial gauges scratched until unreadable, EVA suits worn out exceedingly fast, damage to electrical equipment, and decreased function of the communication systems due to overheating.
So now we're going to go into our actual design. So this is presenting the dust shield integration system that we created, which is set to be, as we said, attached to the Blue Moon Lander. Upon expansion of the system, the shield is going to deter dust from falling on the lander and possibly causing extensive damages. So the shielding itself, which is indicated by the blue material, is made of carbon nanotubes that are going to protect the lunar lander from high velocity impacts from regolith. So likely things like rocks and smaller items. So additionally, the electric charge in the electrodynamic shield, which is integrated within the system, is going to attract surrounding dust, which is going to reduce the amount of regolith thrown around on the landing site, which is going to help reduce contamination for the samples that are going to be collected later on. Here we have a further breakdown of the different components. It's going to feature 4 linear actuators along with a series of beams and brackets, and the electrodynamic dust shield, or EDS as you'll hear us referring it as, which is integrated within the blue fabric. And here, once again, is a further breakdown. We have the EDS fabric in blue, which is, like we said, the carbon fiber nanotubing netting, which has copper wiring embedded throughout. It's connected to the beams, and when the DSI contracts, it's going to fold up against the lander. We also have the different beams indicated by 2 and 3, which is the triangle beams and the diamond beams, along with these center hinges that will connect it to the main structure. We also have the indicated by number 5, the pivots where the linear actuators will be attached to, along with several clamps that are going to hold onto the fabric to allow it to contract and expand.
Hello, my name is Chase, and I'm going to be walking us through the materials and their associated costs. So as we can see, looking at the table, our primary cost drivers are the structural components, and all of these structural component costs were calculated using the cost for the stock size needed, not the volume of the final part. And for parts that were very large, where the stock size needed wasn't available on the internet, the price per cubic meter of the closest size was used. So starting with the triangle and diamond arms, as Elizabeth said, these are our main structural members, and they are made of an aerospace grade titanium alloy that is known for being very light while still remaining very strong. And it was very important to have a very light material because of how large these beams are, being approximately 5.5 and 7 meters long, and with a 60 centimeter outer diameter and a 3 centimeter wall thickness. And then next we have the linear actuator clevis mounts and tube couplings, which allow the arms to connect to the linear actuators and the hinge mount at the bottom. And they are made of a high strength steel alloy. So even though the steel is quite a bit heavier than other materials, it is very strong. And in our structural analysis, which we'll show later, we found that these were critical points of failure and potential points of failure in our design. So we went with steel, even though it was a bit heavier. Next, we have the hinge mounts that allow the system to pivot and retract and fold down. And it is made of a high strength aluminum alloy. And this was chosen primarily to save weight. Also, the aluminum is much easier to machine and manufacture compared to other materials. And with the hinge mount being such a large piece with a lot of material that must be removed, we determined that it was important to keep it as aluminum. And finally, we have the ring structure, which is created from a nickel alloy, which is a relatively ductile material compared to the other materials used. And this was chosen as it can help absorb some of the energy from the other components without fracturing. And it is a very dense material. However, it is a relatively thin band going around the circumference of the spacecraft. And we determined it was very important to have a structurally sound connection to the spacecraft. Next, we have the linear actuators that allow the DSI to fold up parallel to the spacecraft and then deploy at a 45-degree angle. And in order to do this, we need a stroke length of 129 inches and a load rating of 200 pounds for the linear actuators. Now, the largest commercially available linear actuators in that size class are 60 inches long, and they come at a price tag of around $300. So since these ones would need to be custom made and over double the length, we estimate a cost of $1,000 each for those. Next, for the net, it is made of carbon nanotube netting with copper wire running through it. And it uses a little over 400 square meters of the carbon nanotube net with 430 meters of 13 gauge dipped copper wire running throughout it. And finally, for the EDS to work, we need to run 4,000 volts through the wire at a current of 5 milliamps. So we selected an appropriate power supply that was able to do that using an input voltage of 120 volts AC.
Hi, my name is Benjamin Smith, and I'm going to walk us through a contextualization of our design. So first off, why did we choose the Blue Moon HLS? The primary reason for that is that it has a more typical lander design compared to our other option for this challenge, which was Starship. And our team felt that by choosing Blue Moon, we would have a much larger history of data to comb through, primarily the Apollo missions. And additionally, by making our design for a more typical lander design, it could be used on future landers if developed and improved upon. And the second thing to contextualize is, why do we go with a combination of systems? And so when our team started our initial research, we quickly figured out that in order to have a more permanent solution for dealing with lunar regolith, that it would likely require extra missions and a significantly higher cost in order to achieve that. And so we went with something that's more modifiable, something that can be attached to an already existing lander and be sent up there. And obviously it's more of a temporary solution, but we felt that that fit better within the parameters of the challenge itself. And so why do we have this big shield here? And so primarily the shield is an active method of dust mitigation. By deploying, it will help deflect dust that runs up and hits it. And additionally, we realized that the shield, we won't have to worry about any flight characteristics being affected due to the fact that we'll be in a vacuum when the lander is landing and ascending. And why did we choose the EDS? As a passive method of dust mitigation, we felt it was important to include, so that way any dust that's not deflected by the shield would be able to be repelled off the surface of the lander itself. And additionally, it's a low power system, so it would not cause a massive strain on the HLS's current power setup. And we combine these systems together to cover their weaknesses and to improve their strengths.
Hi everyone, I'm Paul, and I'll be going over the astrodynamics of our mission. And so our astrodynamics sequence is a simplified version of the one that will happen for the Artemis 5 mission in 2025. And the sequence comprises of 4 parts, which is the initial low Earth orbit around the Earth as a parking orbit, a translunar burn, an insertion orbit to enter the moon's gravity field, and then a rendezvous sequence to catch up with the HLS system that is already orbiting the moon. And so looking at the Earth orbits, we see that it takes a total of 3 burns in order to get to the blue circular low Earth orbit. The first sequence is the launch sequence, which can be shown in red. And this one uses an impulse of 9,170 meters per second, which puts us in an orbit of 30 kilometers periapsis and 1806 kilometers apoapsis of altitude. Once we reach the apoapsis of this orbit, we perform a perigee raise maneuver. The main purpose of this is to raise the perigee from the 30 kilometers to 185 kilometers. And the reasoning for this is to make sure that when we do a close approach of Earth again, it doesn't get too close to the atmosphere where it would then re-enter. And that can be shown as the green orbit. So then once we do a full orbit of the 185 by 1806 kilometer, we do a circularization burn at the apoapsis again. This one uses 396 meters per second of impulse, and this circularizes the orbit so that we're in a parking orbit around the Earth. And this circularization makes it easier to find a point in time where we can do the translunar burn to ultimately reach the moon. Then once we do the lunar burn and approach the moon, we do a orbit insertion, which slows down our vessel enough to do a circular orbit around the moon. This retrograde impulse is 1919 meters per second. And once we're in this orbit, a transfer orbit is conducted in order to reach the larger orbit that the HLS is at, as it can be shown in the green. This transfer orbit is a Raman transfer orbit, and it occurs at the ascending node, where 177 meters per second of impulse is used to get to our goal of 4,000 kilometers of radius. This impulse also does a correction in the inclination and the right angle of insertion to make sure that the orbits are matched up correctly. So then once we do half an orbit of that one, we do another burn to make sure that it is circularized and matches the HLS orbit. once we're in the same orbit, we realize that we're not in the same positions. So we have to do what's called a rendezvous sequence. And this sequence makes sure that we get put in a similar orbit, but a slightly different one to make sure that we slow down enough in order to catch up with the HLS that's already orbiting the moon. This can be shown as the pink one. And then after 2 orbits of the rendezvous sequence, we reach a point where we ultimately approach the HLS. And this results in a total mission impulse of 15.2 kilometers per second and a total mission time of 2 days and 15 hours.
Hello, my name is Sapna Samaru, and I'll be going over the fluid dynamics and plume effects. So doing the CFD analysis, we utilize ANSYS in order to really mimic and gain the information we deem necessary for our lander. When doing the analysis, we ended up using a mesh geometry due to the complexity and the nature of how the rocket nozzle is shaped. More specifically pertaining to the curvature of the nozzle, we want to make sure and ensure that we get it to the best of our abilities. This enables us to obtain accurate and reliable analysis results, particularly dealing with such a unique design. By completing the CFD analysis of the rocket nozzle, we're able to gain the Mach number profile and the velocity profile for the engine itself. This is important to have because this simulation will reflect real-world behavior and the structure of the component being analyzed. So going on to the engine itself, the engine is using a closed dual split expander cycle. Really what this does, it takes the fuel and oxidizer, heating up the fuel and combining them for ignition, as well as utilizing the oxidizer as a cooling agent on the exterior of the nozzle. Due to the stoutness or shortness of the nozzle itself, the cooling agent is very important to have because it actually increases the ability of ignition and combustion, which in turn leads to a theoretical maximum efficiency of 85%, which comparing to other maximum efficiency percentages out there currently for engines, this engine seems to be one of the highest performing ones currently available in the market. Also, this dual expander cycle is used for the BE-7 engine, which the Blue Moon lander will be utilizing 3 of those engines. Also, this concept is most notably known for the RL-10 created by Aerojet Rocketdyne on the space shuttle and also stage 2 of the Saturn V rocket. This engine, the BE-7, will produce a thrust of 44.5 kilonewtons or 10,000 pounds force. So going on to the plume effects, which is very important pertaining to our project, but being able to have the nozzle gimbal and thrust vectoring control that could be either controlled by the commander of the lander or also AI software itself, we're able to limit the amount of dust or plume effects that are going to be created. Also, another point that is very important is the diffuse gas eruption, also known as DGE. This affects the lander in 2 different ways. One, when pertaining to pressure differential, when the pressure differential from the rocket engine and beneath the lunar surface, the pressure differential actually spread laterally, causing discomfort for the lander when it makes contact with the surface. With the lunar surface already at a 5-degree angle, this is important as we have a limited margin of error. Also, another effect this could have is that once the engine is turned off when we make contact with the surface, that it leaves a crater underneath and due to the collapse of the pressure. In turn, this could also lead discomfort and unleveling of the lander. Also, it is important to know the topography of where we're landing. We are currently landing in the southern polar region. And right now, there are 2 big regions being explored. Right now, Mare Carisium, which a lot of the CLIPS mission in the near future are going to be sent to for scientific research, as well as Shackleton Ridge, where scientists believe we can find ice water over in that region. The issues with landing in the southern South Pole is that compared to the Apollo mission, where they land more in the equator of the moon, that the southern pole is much more rigorous and treacherous to navigate through. So this adds another complexity for plume effects as this is unexplored territory. because of such effects it could have with larger boulders and craters, this could lead to possible material damages to our DSI and even possible damages to the lander itself. The most notable occurrence of plume effects occurring is the Apollo 12, where Pete Conrad landed the LEM Intrepid, we see in the corner right, and went to retrieve parts from Surveyor 3 that was under for 2.5 years and then was abandoned. They landed over 180 meters away, and still when Pete Conrad made his way over there to collect parts, that it was totally covered in dust. Again, it's important to know the landing site and make ourselves familiar with it because they landed in a region on the left near side of the moon called Oceanus Procellarum, which is an ancient volcano site with former flat magma. So it's important to know and discover what effects our lander could have and the role our DSI plays.
Hi, my name is Francisco, and I'm going to be presenting the power systems and control sections. So first and foremost, our objective was to select a battery capable of serving both the electrodynamic shield and the actuators responsible for deploying and retracting the DSI. We recognize the importance of having a power system that operates independently of the lander's main power and reduces the reliance and increases the overall efficiency of the system. To achieve this independence, we opted for a battery separate from the lander's main power source. This decision comes with the added advantage of providing us the flexibility to recharge the 24-volt battery externally, perhaps with a solar panel. Moreover, it allows us to strategically route the lander's main power where it's needed most during the mission. Now, our choice of battery magnitude wasn't arbitrary. It gave us valuable insights into how the DSI would be utilized. Most importantly, we considered the fact that the EDS and the actuators wouldn't draw power simultaneously. The EDS, designed to operate with low current, will be activated when necessary, while the actuators, each at 60 watts, will come into play solely during the deployment and retraction phases of the DSI. So as you can see in this diagram, our dynamic power system plays a crucial role in the success of the mission. I'm going to walk you through the stages of this diagram here. So first we have the landing sequence. As the lunar lander descends, power is supplied to the linear actuators responsible for deploying the DSI mechanism. This ensures a controlled and precise extension of the DSI structure. Second, we're going to have the transition to the EDS activation. Once the DSI is fully extended, power is seamlessly shifted from the linear actuators to the EDS system. And this transition is a critical moment in the mission as it marks the activation of our EDS. Next, we have the retraction sequence. So following a successful landing in the EDS activation, the power is then redirected back to the linear actuators for the retraction of the DSI mechanism. This controlled retraction is essential for preparing the system for the next phase of the mission. And then finally, we have power deactivation. Once the DSI is fully retracted, power to both the linear actuators and the EDS is deactivated. The strategic power management ensures the energy is utilized only when needed. Excellent. So here we have our controls for this system. So first, we're going to see in the bottom right corner the closed loop block diagram illustrating the implementation of a PID controller. So before we can explore how the PID control is employed with our linear actuators, it's crucial to understand each step within this block diagram. So the controller's primary goal, in our case, is to mitigate the effects of error on the plant. So this leads us to three essential control methods: proportional control, integral control, and derivative control. So our PID uniquely combines all three of these methods as depicted mathematically by the equation on the slide. To implement this PID controller with our linear actuators, we've chosen to go with the manual tuning method. It's intuitive and well suited for our relatively simple linear actuator mechanism. So first, we'll start by increasing our proportional gain for a fast rise time and controlled overshoot. And after that, we'll adjust our derivative gain to minimize overshoot and then our integral gain to minimize steady state error. So moving specifically to our linear actuators, it's important to note that there's no computed torque control as these operate in a two-stage manner. And velocity inputs are unnecessary due to their simplicity. So instead, we'll rely solely on the encoder within the linear actuators for feedback control and utilize the position of the linear actuator mechanism.
All right, so I'm Rodrigo Pazanotto, and I'll be talking about the structural and thermal analysis of our design. So for the structural analysis, we decided to separate the system into three different critical components: the linear actuator, the shield arm hinge system, and also the mounting ring hinge system. Right here as the linear actuator, the shield arm, and the ring around. And for the analysis, we decided to focus on the main concerns of our structural design and the material selection and the attachment methods. It's also good to mention that everything was vetted using hand calcs and hand calculations, and the overall factor of safety of all the three subsystems that we separated is around 1.93. But going for the linear actuator right now, our main concern was first the linear actuator bolt bending and shearing under load right here, and the pivot structure separating from the arm. This two brackets right here, as we see, and that's why, as Chase said, we chose a high strength alloy steel, stainless steel, and also we use the titanium alloy pin for this specific mounting bracket system. And you can, what else? Okay, so now going for the shield arm hinge system. So the main concern here was the hinge system brackets breaking off the main hinge system right here. As you can see, we have the different brackets. That was one of our main concerns. The hinge pins, again, just like in the linear actuator, shearing from the weight of the arms, opening and closing, and the arm coupling detaching from the hinge coupling right here as well. And for that, the material selection, as we said, I wanted to save some weight, and because this pins right here, they don't suffer as much as in the linear actuators, we're able to use aluminum alloy, and the factor of safety of this specific system is still at 2.4, so it's pretty safe. And for the attachment method, we decided to use plasma welding for those systems, and the titanium alloy pin again for the hinge systems, and the plasma welding just because it minimizes distortion, and it's just better overall when you're dealing with spacecraft components. And now for the mounting ring. Okay, for the mounting ring, our main concern, since it's this is the part that's going to be connected to the HLS, so we need to make sure that it's going to stay there. It's not going to fall off during a landing procedure. That's why we use the nickel alloy Inconel 718 for the material selection. As we said, our main concern is the detachment of the hinge system via the breaking off of the mounting ring and or the HLS as well. And the attachment method also is the plasma welding. Okay, so for the thermal analysis, we decided to mainly analyze the shield arm in this case, and the parameters that we use for our simulations. Of course, the material of the shield arm, which is titanium, and the assumption of the ambient conditions of the Apollo missions, since it's where we have all the information coming from, at a temperature around 66 degrees Celsius. And our simulation said that the thermal load concentration, there was a concentration of heat flux around the bolt holes in and out, and due to the discontinuity of the design, just as expected, but it's still not of a concern. And we realized that the main concern also was coming from heat conduction and radiation. Conduction just coming from all the mechanical systems, operating electronic systems, and the radiation from solar exposure. But also realized that the plumage and the regolith could cause the heat convection to the shield during the landing procedure as well.
That's
He's watching.
You guys
Yeah,
can clap
250
for yourself
loud.
if you want. Bigger questions.
I was trying to rush so bad.
I made good time. You guys are all late too, so you have a few minutes to spare.
Oh, oops.
Okay.
Great job.
Once I post the questions.
No questions? Okay.
Everybody gets zero.
Zero.
We didn't do a good enough job to inspire questions.
You guys need to wait. Patient.
You can probably pull up the chat on your Zoom.
Yeah, I was
so you
thinking-
can look at the board.
It was Alt Control H.
Control Shift H.
Control.
I've done it so many times.
Yeah, there we go.
I don't
Oh,
understand
there's
why it doesn't just
4
automatically
comments
go
now.
away.
So first
Sometimes like auto
question,
hide and sometimes.
first question, your shield has gaps. How acceptable are those?
Oh, so,
You can go back to the.
yeah, I'll go back up. I have it on my iPad just so I can, oh yeah, you can pull up the picture.
Yeah.
So the
Chat.
gaps
I mean,
were,
yeah.
it's fine to keep the chat open because I have it on here. So the gaps were something that we couldn't,
Don't worry.
yeah.
You're good to explain.
So these gaps here are for the legs of the lander. We realized that if we wanted to have a good protection from area for the shield, that we would need to have it as low on the lander as possible. And to get that low, the legs would interact with the shield in some way, so we made those cutouts. Obviously, we don't have the final dimensions. The model we use for the HLS for our SolidWorks could be outdated. And so just the idea was that for the legs moving and for the shield moving, that we wanted a big enough gap here. And for these smaller gaps down here, though that's kind of a limitation just of because ideally we would have the shield go all the way down here, but when we were modeling it, we found it pretty hard to get that extra segment covered there. And so yeah, and along with that, when it's descending, the engines in this area, so there's a certain the rocket plume should displace it enough that if there is any dust that comes through here, that the EDS can take care of it.
And he's got another
Oh,
question.
sorry.
Just wanna let you know.
I'm pulling up the slide that has it attached to the lander just to make that a bit clearer.
Yeah. So while she's trying to find that, we're trying to help protect the lander from any displaced plumage that will be displaced by the engine. And then additionally, having the shield at this angle should have any deflected plumage go up a bit. So if there is any structures nearby, then ideally the plumage won't won't be hitting it directly. It may just fall on it, which isn't as big of an issue considering the low gravity environment.
It should also be noted that the physical shield itself is meant to block the larger regolith, while the EDS that is integrated within it is what's going to protect from the smaller plume that'll be appearing during the landing. I hope that answered your question.
So how effective will this be? That's a great question. So we designed so we designed the shield around the idea. So the number we had for the HLS was that it had a base diameter at the bottom here of about 8 meters, and so we wanted to have a protective area go out to 16 meters. So basically double that. So that's why the size of the shield, it's pretty large in that I would say this should be fairly effective. I'm saying that with 50% confidence. With the angle we chose, so we chose a 45-degree angle. We could have gone with a lower angle to deflect it at sharply more out. But we felt this angle was good, that any dust will kick off it, and the lander will still be moving. So it should any of the lighter pieces that if they miss this or if it's still in the air and the lander's moving with it, EDS will grab those and the shield will knock the bigger pieces away.
Along with the fact that EDS has, with the studies that we've read, has been proven to be a pretty good method of mitigating dust on different objects.
So what is the measurable objective? How do we know we achieve it? So in our case, I would say the measure, if we had to design, if we had to design a test for it, I'd say it'd be like if we measured how many regolith particles were on the lander with the shield and without the shield, then that would kind of be the test, and see the percentage drop in the number of particles on there. In addition to that, we could also look at, if we were able to physically test it, we could determine how much lunar regolith the shield can deflect, and maybe particle sizes that it can go up to, or if it can cover all of it, or if there's like a super big chunk, maybe it's not good enough, but that's what the linear actuators are there for, to help keep the shield in place. And yeah, I
get that. Also, to answer your question, what's the measure objective? When we're looking at former landers through the Apollo mission and their LEMs, a lot of the maintenance or electronics is located at the lower level. So of course that's going to be reachable. Or Blue Origin, when they have their final mock-up and construction of the lander, they're going to know how to accommodate the astronauts to go around and fix the any electronics or any instrumentation that they could have on the exterior as well. So that's when it comes to how do we know we can achieve it, that's also a main goal of having the DSI at that specific angle and having it block.
Ding it, Sasha.
You're out of time.
It's okay, keep going.
Yeah, so it's gonna block majority of the, if not all, the instrumentation, again, because we, as Ben stated earlier, with the spaces, it's just with the CAD, it was giving issues. But that's also a really important thing to note, because I do not believe that our astronauts could jump onto the cabin bay from ground level or the platform. So that's also something important to note as well.
I think just another thought of what like Tom was trying to address as well. Is there like a certain percentage of like displaced lunar regolith and how it actually ends up resulting in either impacting the shield or the spacecraft itself? Like, is there a predetermined like percentage in which you would which is allowable that won't actually cause any damages towards the system, especially like maybe percentages involved with like specifically like more sensitive areas, which Tom might actually ask that in a second, but just out of curiosity, like, do you guys have a primary objective in that regard?
So regarding plumage, as I believe Katie stated earlier, and again, the South Pole is like Columbus coming to the Americas. Like it's never been discovered really before. We haven't, until Chandrayaan 1 or 2 that was landed in August, nothing was really down there. So it's still new land. So we do not know how deep the regolith is really compared to the equator where Apollo missions are.
What I'm trying to refer to is like, is there an actual quantity you're looking for in that in terms that you find safe?
So based on my experience I've had with CNT, it's been able to handle a high volume of lunar simulant per se. So that is, as to the percentage, Ben, are you able to expand on that?
Yeah, I was gonna build off what Sachin was saying. So ideally, the way we would go about it is we could split up the HLS into different sections with allowable regolith impact percentages. And so for pretty much this bottom half of the lander, we'd probably want less than, I don't know, 10% maybe, probably lower. Just kind of building off what you were talking about. And anywhere with, or we could break it up by critical systems where they're located on the lander. And those areas we would measure to see if the shield had a noticeable effect when it was deployed compared to without the shield. And that's the way we could measure it. We don't have exact percentages because that's kind of like something that's like because the research we've done about the lunar regolith hasn't really given like a percentage of like, oh, like this panel is like 98% of it is covered in regolith damage or whatever. So
I guess it is quite a complicated question, but
Yeah.
I guess it just kind of comes down to like the fact of like its own I don't know if factor of safety is necessarily a good term to put to it, but just in terms of like what range of potential impacts would cause
Like the limitations of each.
the limitations. Yeah, exactly.
Yeah.
So to kind of answer your question from what I'm getting from, for the percentage of how much it could withstand of lunar regolith, that's why we accommodated with a 4 kilovolt battery at a lower amperage, which the EDS will work best at that. When we deploy our shield while on descending, so it does not just deploy once it lands. So accommodating that 4 kilovolt battery, it allows us to actually continuously run the DSI. So therefore, when it comes to the limitation, because it's continuously running, it's expelling at the same time it's gaining plumage on there as well. So it's gonna be somewhat like an on and off situation where the lunar regolith kicks up on there but goes off. But again, as we're landing, the plumage effects will keep kicking up and going back down.
Yeah, because a big concern, especially Tom was bringing up in terms of like the gaps, which is kind of I find a little bit problematic because once you are at a very close impingement with the surface, you're going to get some crazy turbulence.
Yep.
So you're going to get a lot of kickback, especially directly back up. Now, most of it's going to be dispersed outwards, but you're going to have a centralized region of a higher density of plumage that might interact into those sections. You might get a buildup back in within that cone. But anyway.
I mean, yeah, that does sound like a really nice PhD thesis. But
because I think one of the most difficult things when modeling this would be it'd have to be a combination of modeling like the physical regolith, but also somehow integrating the electrodynamic dust shield itself within the model, which I'm not sure how within our limitations as undergrad students trying to figure this out.
No, I know. I'm
Yeah.
just...
but it would definitely be an interesting thing to model. Yeah.
And to speak on the gaps, so a big problem we had, when I was working on the CAD for the shield, I nearly lost my mind trying to figure out how to model the fabric part of it. I ended up using a 3D sketch. But in an ideal, to make, this is our close model, but ideally the fabric would go as low as possible to the base of the lander itself. And so, but that was just even more hard to model when I was doing it. So, so realistically those gaps shouldn't be there, or they would be even smaller.
I remember you telling me about this. I do. Okay, I'm sorry about that.
No, it's okay. Yeah, it was a nuisance.
Yeah.
I spent I spent like 2 hours trying to like make separate pieces of the fabric and like set them at angles to each other, and that was a very bad idea. But yeah, no, that's true.
Also, if I'm starting to sound like my professor, there's a good reason why he berates me quite often. So apologies if they're really hard questions.
We mentioned astronauts.
So
this
this was something that we had addressed. We were discussing this based on the limitations and the fact that we don't have an actual model of what the lander looks like. There would ideally be a gap within one of the quadrants of the net in which
a place to disconnect.
Exactly. In a quadrant in which the astronauts will be able to open the net itself and exit the vehicle. But again, because we don't really have an actual model, it's hard to be able to see forward and see what that's actually going to look like.
Yeah, so the idea would be that you could detach a segment of the shield to open the door. But like Elizabeth was saying, we don't even know like how they're gonna open the doors on Blue Moon. Like, are they gonna like swing out? Are they gonna like come just straight up? And if it comes straight up, cool. if it swings out, then like we would just have to, deploy once they've landed, they could just deploy the shields at a sharper angle, so they would need a bigger linear actuator. So stuff like that. And I guess as like a tangent to that, we have this attachment ring on the for the system, but how would that be done? How's the fabric? And is it manipulatable by someone in the spacesuit? So they wouldn't manipulate the fabric directly. It would be kind of like not like a pin system to it. But
Modular?
yeah, it would be modular in a sense that there would be some kind of connection there that they could access from the door open, and that they'd be able to like click on something or like undo a class or something like that. And maybe there's like 2 of those at like the base of each, and then that drops the whole set or opens the whole segment up. And obviously it would have to be designed to work with a spacesuit. That was another thing that was like we couldn't like really model in SolidWorks just because like it started getting complex outside of that. Is the attachment not in the scope of this design?
I think again, as of right now, that is a feature that we have to manage once we are aware of what the opening system of the lander is. Based on that system, there could be several possibilities for a solution. So again, that modification is available, but because we don't have the exit system as of now, we can't really speak on that
with confidence.
With confidence, yeah.
Yeah, because the door could be moved up higher or something.
I mean, if looking at, for example, starships, I think the first concept art we saw, they had almost like an elevator, and that's something that I'm at least not very familiar with, but it's because of its size. Yeah. And so with the uncertainty of how this lander is gonna, I guess,
final design
exactly.
Lander. Yeah.
Is potentially making it so like these this dust mitigation device could extend further down and angle down. It's got like a little stairwell on it or something.
That could totally work too.
Be implemented with the stairs to get down and up and down. If there's like human habit, or at least a habitat somewhere in the lower section, but I doubt that. I actually have looking at the design, I have no idea where people would be.
Well, yeah, I mean, one of the things was that, one of the things that we were worked on was, what angle we wanted to have the shield at. And that was a big thing with figuring out the linear actuators and, what distance they needed to be. But you could totally adapt this to push down even farther. And if you maybe had the linear actuators on like a slide system, you could have it slide down and push out, so then it's in a completely down position, and then the stairs go over. That would work.
Yeah.
Or if the access door is like at the top of the spacecraft, you could fold the DSI back up, and then
which
answers
answers
for a couple minutes.
Which answers Tom's next question, in which the fabric is stood parallel to the rest of the lander.
What is the fabric doing in the stowed position?
Yeah, it's essentially, in the most basic form, similar to an umbrella. When you close up an umbrella, it's parallel to its inner rod. It's the same idea, in which it's not top, that's well. Well, in its stowed position, it's not being held taut. As far as we know, it shouldn't present any problems.
We're not dealing with air-rich environment, so
folded
drag and we could, for like rockets, they'll fold parachutes in a certain way such that once the deploy charge is activated, it unfolds perfectly. So maybe we could do a similar setup with the fabric, or when it's folded, you can maybe put like a clip or something very loose that would just snap off just to kind of, yeah, I know it's not a parachute, but
we also aren't really expecting the fabric to be experiencing any extreme forces while in the closed position. Upon a certain altitude is when it's going to expand, and once it lands, I guess you could say, it would be able to contract. So it's not really at any point seeing any extreme forces. The most extreme forces it'll see is during landing, which is going to be expanded.
Also based on the way, how to say it, I guess the CNT sewed is not really made to be flexible unless made very, very small. So that's also something to take into account. It's not gonna be really that floppy based on how it's sewed and how it's installed as well. Because at the end of the day, we are using the carbon fiber, and so having those characteristics and structural characteristics, that it won't be floppy per se, but there is room for movement.
Yeah, I mean, that's how we designed it too, was to in the compact position such that it could, fit in the New Glenn. I think
New Glenn, yes, that's how it's going.
You are reusing the HLS though, so it might be a problem that you have to refold it and unfold it. Unless you're just going to maintain it being unfolded the whole time, it might just be a little bit worrisome in terms of just usage over time. Like, I mean, there's no atmosphere, but there's still enough of a dynamic forces that there could be issues.
Yeah.
With it being floppy, is it possible perhaps that you could like develop a system that is similar to like the ISS radiators, where it's like a structure of like an origami type structure, where it's being given a little bit more structural integrity with like cross lines or something like that?
Oh,
we could probably integrate crossbars to kind of like
just
essentially guide it as it folds.
Yeah,
or like a system that kind of retracts the
fabric.
the fabric inside the shield arm as it unfolds, or like as it folds back in, so it goes inside the shield arm, like
like a roll, one of
like
those
a
rollout
roller,
posters,
yeah, exactly.
almost. That could, something like that could also work. I had something and then I lost it. Oh,
Get it back.
I'm trying.
Any questions, Ting? You've been quiet over there.
I'm waiting for Tom to ask all the questions first. Yeah, he's a guest. Let him ask.
Yeah, I'm rude and I interject.
The dynamics of the lander and the fabric poles while you're landing.
So as far as I'm aware, I think Paul, did you do the structural analysis, like the Hancock's and such?
Yeah, I did.
Yeah, so those things were accounted for, I believe, when we were doing all of our structural analysis. And everything appeared to pass the, I guess, project qualifications. Nothing failed based on our material selections and design choices, if that answers your questions.
And if you're more so talking about the flight dynamic, like how the lander and the fabric and the poles are behaving, what frequency are they going to vibrate at? Is that a problem for the lander structurally and control wise? Okay. Yeah. Yeah. Just as I was like, okay. So once we're in our final orbit for the HLS, there's a couple ways we've talked about going about it. One of them was just that we could deploy as we're descending, or have like a altimeter type thing, using LiDAR to detect when to deploy. But the force, how much was the force again for the linear action? Oh wait,
They're 200 pounds.
200 pounds.
But it didn't
deploy. Yeah, and it was
quite that much.
we planned to deploy it over, I think, what was it, 2 minutes?
It takes 2.5 minutes to deploy. So
ideally, we would be deploying the shield, so like the fabric and the poles, at a point where the lander is just starting its descent. so it won't be going as fast as it should be, I believe was yeah, because we said like a height of like, what was it? Like 1,000?
I think it was 1,000.
Yeah, but I
Yeah.
feel like that would, also be more based on having the time to.
Yeah, knowing the distance, so in that. Is that going to set up? That actuates a thruster. Is that going to set up a vibration? Oh, if the linear actuators are gonna create a vibration from actuating.
Well, I also think he's asking if like the actual landing sequence, because the individual thrusters are, I guess, activating.
Okay, yeah. Yeah, I mean, we'll have vibrations from.
In general, you have vibrations. Like you just can't ignore that when you're landing on the moon or in space. So that's something the Apollo missions have done. They have data that backs that up. It's very hard to limit it. When it comes to the actuators, again, depending on the altitude that we're at, extending the actuators, that vibration will be very minimal, because also at the end of the day, we could help somewhat combat that by thrust vectoring with the three different engines as well. And there also is going to be I forget what they call it. You know, the little
Cold gas thruster?
Yeah. The thing, the little pulses. The word's not coming.
Or the RCS.
Right, there we go. Yes,
Oh, yeah.
the RCS too. So we have those to also accommodate for if any, for like dampening vibrations as well.
I think that also once we start getting this mission is set to be in 2028, likely to be later, but once we get more mission details in terms of, I guess, what exactly is going to be happening, that could be accounted for in terms of adding damping to different locations to help with the vibrations.
Yeah, and even, maybe we decide to deploy them slower to reduce the amplitude of the vibrations. So, jump it from 2.5 to 5 minutes, so it deploys very slowly. And, we have the thrust vectoring, and since it's rotationally the same, then, I mean, we could have some resonance, but I think the vibrations from the actuators can be accounted for with some proper planning.
Well, that's why America has some of the brightest minds.
Yeah, that's not a us issue.
I'm gonna have some.
I mean, these were just key points that as we worked through our report, they were elements that we were asked to find, and we found that they were just relevant to fully understand the mission that the lander is going to be experiencing. Also, just to give proper background on why it is that we're doing what we're doing in terms of background on lunar regolith and the proposal. Yeah, I think it just gives the customer a better background overall.
Well, Earth orbits. We're doing 2 orbits before we enter TLR.
We perform a total of in the parking orbit, we perform 6 orbits in order to like time the maneuver time, and then it takes 2 orbits to actually get to the orbital thing. But in terms of why we included in the presentation, it's more so background knowledge to understand the actual mission of this of the Artemis 5 mission.
Can you swap it, CFD?
CFD just had 23.
Yeah, and on top of that, I guess we wanted to give the full picture because the actual point the lander will be coming in from, with regards to its position on the moon, is going to be part of the transfers, and so we wanted to, I guess we may have been a bit too detailed showing the Earth transfers too, but we felt that it was good to be very thorough. So CFD, so this was for this CFD was modeling the how the BE-27
B7.
BE-7 the BE-7 engine and this top the CFD graph in the middle is the Mach number, and this bottom one is the velocity. And so this CFD was set up. Oh, okay. We set up the CFD to simulate a low pressure environment. So like typically if you do CFD for a half rocket, doing a half nozzle, since you can just mirror it, you usually set, you'll have, some ambient pressure here, and then you'll get, a couple shock diamonds. But since we're in space, we set it up to have a very low ambient pressure, and that's the what we see from the results is that there's no. Why do we do CFD analysis? So we did the CFD analysis to get an idea of how the exhaust will, like the characteristics of the engine exhaust, because those characteristics would impact how the lunar regolith would behave. Yeah, and if you want to.
So also something to take noted on the CFD analysis, it helps us understand one, most importantly, the plume effects. We're seeing the diamond shape, or even with the ambient temperature conflicting with the exhaust, that we need to understand when we ignite our engines, the 3B7s, what kind of effects are we gonna have when we're trying to land and descend? So that helps us kind of understand as to the kick up and the plume effects. Again, as I previously mentioned, the DG as well. That's probably one of the most notable things, because you want to be able to land safely. And this is something we have to take into account when we're going to land. Also, it helps us understand based on those plume effects as well, as to when and the altitude to deploy our linear actuators in order for the shield to start blocking any plumage kicking up.
Yeah, and one of the things we had talked about, but we weren't able to really dig into, was doing like a particle simulation of how the exhaust plume would displace lunar regolith. We weren't sure how to simulate that, but at least having an idea of what our exhaust velocity would look like was important for us to consider how, if our shield, primarily the angle it's deflecting at, what we can expect the particles to be moving at once they've been displaced due to the gas and the force that the exhaust will exert on the lunar regolith.
Also noting again, the landing site is very important. We're going to the South Pole. Very larger boulders, larger craters over there as well. So having an understanding of the cone can help us determine, okay, at what point or how close, even though it's the engines are throttlable by the commander or by the automatic system, as to what boulders can be picked up at what velocity. That is information. Again, we would like to have a lot of money to get the simulation to do the particle analysis of that. But again, it helps us give us a base understanding of what we're going to be facing. I mean, when I presented this, it kind of jumped into the plume effects. That's what we related again, it's a base understanding. So we're just trying to get a gist. We're just, okay, so I mean, for how I interpreted was just a base understanding as to what effects it could have. That's what just my personal analysis.
I think that the propulsion system again, it wasn't something we should have elaborated more on it within our slides, but it was something that understanding the plume effects and essentially how far these plume effects would start affecting the lunar regolith is something that also determined at what altitude we would be deploying. It's fair for you to say that. I mean, we should have included
We should have drawn
exactly how
connection.
we should have included exactly how it tied in, but essentially understanding the propulsion system and using the CFD and understanding the plume effects is how we decided the altitude. We just didn't make that clear.
Also, on that note too, something that we should have done as well, we only analyzed one engine when it came to the design, when realistically at the time of doing this, we should have done the 3 engines analysis for that, because that, again, that would have been very impactful and helpful for our design. Due to pressure differential, correct.
Yeah, when it lands. Yeah.
What do you mean by cleavers?
I don't know if you could
I
hear
think that might be referring to like the gap on either side of the middle one. Okay.
Well, that is just, I'm gonna ask for Ben or Alec, because I don't know which, I think that was Ben's design. But, I'm guessing it's because we reutilize, the arms for each of the 3 hinges. And one of them has a bigger cleavage than the other, cleavage than the other. But we could have expanded that pin joint there just to make it fit better. But yeah, that's a small thing. We just realized actually.
Correct,
Yeah.
yes. Yeah. So we did double shear calculations to figure out when the pin would shear. Yeah, that does make sense for it is loaded more like a beam.
It's a small fix though.
It's still
Should
something
be
to be
done.
accounted for.
Yeah.
Mhm.
We can round those. Yeah. Yeah, that's, yeah, when we were putting the CAD together, the geometry of the fabric was really annoying, so we I forgot to fill it with some things, so my apologies. Oh.
That's for the ring. I think that's the
Yeah,
next.
that's
Yeah.
This was the T6 aluminum alloy.
Yeah.
yeah.
Yeah, it's the ring
So-
going around that has the Inconel.
There's no equations.
Yeah, because you
Yeah.
did all the hand calculations.
Yeah,
And he
I
didn't-
mean, the other group, they all can show their kind of calculation, why you cannot. I mean,
It-
you spend so much time talking about the thing that is not really related to how you make your desk. And now you say you don't have time to talk about calculation.
Oh,
Yeah.
Yeah, if you go to the previous slide.
It's not.
No.
There we go.
Okay, so the main structural analysis we performed was for the two pins at the bottom and on the top. And we did fail to mention the equations here, but we did get a factor of safety. The bottom one, I believe, was 1.9.
1.93.
Yeah, 1.93, and then for the top one, it was
2.4.
2.4.
Yeah.
So for the mounting ring was 6.7.
We were just, I guess we could say that we were afraid of putting throwing too many numbers onto the screen and cluttering it. And so we found it might be more valuable just to show that these were the key locations that we looked into, and they all passed the, I guess, primary qualifications that we had. Had they failed at any point, we would have shown, I guess, our iterations and why they failed and the improvements that were made. But within our primary designs, these all succeeded.
And we may not even, depending on the final design of a land or a ring like that may not even be necessary for final implementation, so.
Yeah, going through, we made several iterations, kind of going through and trying to minimize material as much as possible, and until we got to a good factor of safety margin. We were aiming for like the between 1.5 and 2. I believe in class we talked about, for a lot of aerospace applications, 1.5 is the target. I don't know if you had an actual requirement.
Get a minimum and a maximum. Yeah. Yeah, we actually had, there was a part we did, who was it? I was working with someone on structural and we had a part that was over and then we shrunk it. Was it?
Yeah, we did
Yeah.
that with several of the parts.
Yeah, okay.
Mhm.
Oh, well, the ring is, yeah. We didn't shrink the ring. That was only one, but the ring's a little.
Yeah, for the pins, I believe the chosen size we chose was because of that. I believe our first iteration had a very high
Yeah, we
factor of
had,
safety.
yeah, I
And
think
then through iteration, we lowered down the radius of pins, and we also chose the material for it.
Yeah. Yeah, that's for the pins. Yeah, but for the ring, yeah, we could have shrunk the ring. The mainly the thickness of it.
I believe the limitation with the ring was the size of the actual arms, and that our mounting bracket is already designed as
Yeah,
as possible.
yeah, that there was that too. That made it a little tricky. So margins of safety versus required. Okay, that makes sense.
Okay.
Yeah.
Okay.
Yeah, so the plan was, or the idea was that the ring would be welded on or attached to the lander in some way. And that's why we kind of talked about earlier. Based on the final design for the lander, you could maybe just remove the ring entirely. And partly, the ring practically attaching it to the lander, I think from our view kind of was an easy way to attach it, but also it was an easier way to attach in SolidWorks to the lander. So and we thought that by having the ring, it's something that could be. So there's a ring attached to the vehicle. How do
It was welded.
welded? Yeah, yeah.
What was that plasma welding?
Plasma welded.
Yeah.
Oh, it says it right there.
Yeah, yeah, yeah. The yeah, I lost my train of thought again. Love that. Yeah, but like the other aspect of having it attached to a ring was that they'd be able to work on the shield by itself without having to interact with the lander. So manufacturing wise, it might be a little easier. Clevis is welded to the.
Yeah, I also believe that that's plasma welded. Rodrigo, right? The
clevis
is welded to the ring, correct?
The what, sorry?
The clevis.
Yes,
Yes.
yes, the pins.
Reach
Yes.
it. No, the clevis to the attachment ring.
Oh, yeah. It's, plasma welded, in that case, yeah. I'm assuming.
Yeah.
Can you?
That's what, well, that's why you need to, do all the plating first, and all you have to do some preparing, right? At least that's what the research I did. And it was possible with the materials that we chose.
Yeah. What was the process you read about?
Ink canal. Wait. Now I'm confused. The plate to the ring.
Yeah, mounting the clevis to the attachment ring.
Mm-hmm. Well, we will need probably filler materials for sure in order to make that happen. Yes.
No.
No.
Wait.
Go to that slide.
Can you get it? Because I think you get it.
It's this one, sorry.
Let's see if I can find whatever. I have it though.
It should be cited
Yeah, it should be.
in the PowerPoint.
No, in the report. I think the report.
Which report?
Body structural.
Oh, I have it.
Using the attachment methods.
What are you? What are you?
Yes, from what I see here, plasma and tech welding will be, you know, feasible to perform with the aluminum alloy and the Inconel as well. Both plasma and tech again. Well, oh yes, that's what I meant. Yes. From our research, at least that's what it.
Citation.
These kinds of welding can be even completed in space and show for various March 15. 16, 15. Well, it's called Welding for Space Travel, the Ultimate Challenge.
Oh, slide 35.
This is
Yeah,
the-
this is no.
This picture is indicating the heat flux and marks the maximum heat flux at the bolt holes based on the convection and radiation that it's going to experience.
Yeah, good. Go on scale up. Yeah, that's
It in hindsight, yeah, it should be for one higher resolution and two show the scale clearer to more clearly indicate where the heat flux is mainly concentrated at.
Okay, thank you, Tom. Thank you very much for your suggestion and questions and everything.
Thank you for
Thank you.
attending.
Thank you.
Thank you.
Okay, I think I completely agree with Tom. The biggest problem is that the functionalist. How many of you were in my presentation lecture?
Oh, which one? Sorry.
The lecture about presentation.
Oh, well, I wasn't.
No, I was out of town.
wasn't
So you were the
sure.
only one in the lecture presentation.
Yeah.
I had emailed you about the excessive doctor's appointment.
Yeah, that's I emphasize so many times in the presentation. Actually, it's like, you really need to know in 30 minutes presentation what are the core information you want to put in the presentation. The most important information related to your design, your actual design. And I even gave an example that in previous month there was one group that skipped structure part but put a lot of unrelated information in the presentation.
Yeah.
And this I was like, where I mean the whole structure is the only thing I heard, the only value I heard is safety factor 1.9. I didn't see any like what kind of stress you are calculating, what is maximum stress you have, what is I mean the purpose of capsule senior design is not really, oh, I want to design this in this way, I want to design this in this way. That part actually is, I mean, the main purpose, we want to see your logical thinking and critical thinking. I mean, why you design this way, that is more important than the design itself. And I mean, structure analysis is a very important, like why you design the structure in that way, is it safe or not? Show me the analysis, show me the calculation to prove it. It's not like, oh, safe factor 1.9. I mean, show me. So that is the biggest problem, and I think people are waiting outside. So yeah, just work hard and find a report. Yeah. So I think that's the comments I have. So thank you for your presentation. I will ask you.